Good day everyone. In this video, we will go through a problem set on integration. In the first part, we will evaluate the following integrals. Then in the second question, we have a word problem on rectilinear motion. That's a word problem involving the velocity function, acceleration function, and the position function. For the third one, we have a problem on the first fundamental theorem of calculus. In the fourth problem, we have questions on the perimeter or the arc length, area, and volume. In the fifth one, we have a volume problem, and of course, we have our true or false questions. Let's start with the first integral. Let's evaluate the integral of secant of theta all over secant of theta minus tangent of theta with respect to theta. First thing that we can notice is that we cannot split this fraction here since the minus sign is in the denominator. So one good way to tackle this one is either through a u substitution or we will do other manipulations. As we can see, there are two secants here. However, if we let u to be secant theta, we will have a big problem. First, how will we write tangent of theta? And the second is, if we differentiate this one, we have secant theta, tangent theta, d theta, and as we can see, we do not have that in our integrand. So instead of using u substitution, let us try to do some algebraic manipulations. So first, what we can do here is multiply the numerator and denominator by secant theta plus tangent theta. So we have the integral of secant theta all over secant theta minus tangent theta. Then multiply the numerator and denominator by secant theta plus tangent theta all over plus tangent theta d theta. In the denominator, what we will have is the difference of two squares. So that's secant squared theta and in the numerator, what we'll have is a secant squared theta plus tangent theta. And this one right here, this is a famous Pythagorean identity, but in case you don't remember, let's start with the very basic one. Sine squared theta plus cosine squared theta equals 1. Since what we have below is a secant squared theta and a tangent squared theta, what we need to do here is divide both sides by cosine squared theta. So dividing both sides by cosine squared theta, what we'll have on the left is a tangent squared theta. Then cosine squared theta over cosine squared theta is just 1. And in the right side, we have 1 over cosine squared theta, which is just the same as secant squared theta. Then transferring this one to the right side, we have 1 equals secant squared theta minus tangent squared theta. So this entire thing right here would just be equal to 1. And so our integrand will be the integral of secant squared theta plus secant theta tangent theta d theta. And this integral should be familiar to us. The integral of secant squared theta is just tangent theta. And the integral of secant theta tangent theta is secant theta. So that's tangent theta plus secant theta. And don't forget your plus c. So that's the first problem. For the second one, we have the integral of 5 raised to x times e raised to the hyperbolic cosecant of 5 raised to x multiplied by the hyperbolic cosecant of 5 raised to x multiplied by hyperbolic cotangent of 5 raised to x. As we can see here, the innermost function is a hyperbolic cosecant of 5 raised to x. And if we let this one to be our u, the du that we will obtain is first the derivative of your hyperbolic cosecant, which is negative hyperbolic cosecant of 5 raised to x times the hyperbolic cotangent of 5 raised to x. But you have to multiply by the derivative of the one inside, which is 5 raised to x ln 5. And don't forget your dx here. So what we did is we let this one to be our u. And our problem is how to write all the remaining stuff here in terms of u. As we can see right here, we have du equals negative hyperbolic cosecant of 5 raised to x, hyperbolic cotangent of 5 raised to x times 5 raised to x ln 5 dx. And this one right here, the one that we underlined, is actually this part. It's this one. This one right here. So what we can do is divide both sides by negative ln of 5. So we have negative 1 over ln of 5 du to be equal to 5 raised to x hyperbolic cosecant of 5 raised to x hyperbolic cotangent of 5 raised to x dx. And so, what we'll have is first your e raised to u. So you have your integral of e raised to u. And this entire thing right here becomes this one times negative 1 over ln 5 du. And since this is a constant multiple, we can put this outside. So we have negative 1 over ln 5 integral of e raised to u du. And the integral of e raised to u is just itself. So we have negative 1 over ln 5 e raised to u plus your constant c. But wait, we are not done. Remember that the one in the problem is in terms of x. So we will plug back this one right here. So we have negative 1 over ln 5 times e raised to the hyperbolic cosecant of 5 raised to x plus c. Okay? For the third problem, we have the integral of the absolute value of x squared minus 1 dx as x goes from negative 2 to 2. One good thing here is that our bounds are just the negative of each other. And if we are lucky, in case this one is odd or even, we can simplify our integral. So first, let's check if the integrand is odd or even. So if we let f of x to be equal to the absolute value of x squared minus 1, to check if a function is odd or even, we will just check f of negative x. So f of negative x is just the absolute value of negative x raised to 2 minus 1, which is equal to the absolute value of x squared minus 1. And as we can see, this one right here is exactly your f of x. This one is exactly your f of x. And so, we have shown that f of negative x is equal to f of x. And so, we say that the function is even. So, f is even. And if you recall, if f is even, then that means the integral from negative a to a of f of x dx is just the same as twice of the integral from 0 to a of f of x dx. That's something that we have discussed in lecture 4.4. So, this one right here can be simplified into twice of the integral from 0 to 2 of the absolute value of x squared minus 1 dx. Now, this is our problem. We have an absolute value of x squared minus 1. And what we have to do here is identify what the sign of x squared minus 1 is within this interval right here. So, let's talk about the absolute value of x squared minus 1. So, this one would be equal to x squared minus 1 provided that x squared minus 1 is greater than or equal to 0. And it would be the negative if it is not greater than or equal to 0. So, let's just put elsewhere. So now, to determine what values of x would satisfy this inequality, let's solve this one. So we have x squared minus 1 is greater than or equal to 0. That's just the same as saying that x squared is greater than or equal to 1. And this one will happen. This one will only happen if your x would be greater than or equal to 1. You can see that, for example, if we try 2, then 2 squared equals 4, which is greater than or equal to 1. Or, another option is if this one is less than or equal to negative 1. So, for example, if you have negative 2, if you square that one, you get 4, which is greater than or equal to 1. So this one will happen if x is greater than or equal to 1 or x is less than or equal to negative 1. Let's see what we have right here. Our bounds is from 0 to 2. So our bound or our interval right here is the closed interval 0, 2. We will use the positive 1 if x is greater than or equal to 1. So, in the interval 1, 2, because this is the interval which corresponds to this inequality right here, what we have is that the absolute value of x squared minus 1 is equal to x squared minus 1. However, for the interval 0 to 1, clearly, x is no longer greater than or equal to 1 in this interval. And x is not less than or equal to negative 1. And so, it will fall in this criteria, which is elsewhere. And that means your absolute value of x squared minus 1 would be equal to the negative of x squared minus 1. And actually, this is just the same as 1 minus x squared. So, our integral right here will become multiplied by the integral from 0 to 1 of 1 minus x squared dx plus the integral from 1 to 2 of x squared minus 1 dx. And now we can easily solve this one. 2 times the integral of 1 minus x squared is just x minus x cubed over 3. And we will evaluate this at x equals 0 to x equals 1. Plus, for x squared minus 1, we have x cubed over 3 minus x evaluated from x equals 1 to x equals 2. This one here would just be some dirty arithmetic. We have 2 times, for the first one, we have, wait, let me change this one to bracket so that it will be a little bit clearer. So, first, at x equals 1, so we have 1 minus 1 cubed over 3 minus, we will plug this one now, we have 0 minus 0 cubed over 3 plus, for this one right here, we have 2 cubed over 3 minus 2 minus, at x equals 1, so we have 1 cubed over 3 minus 1. Okay. So that's 2 multiplied by 1 minus 1 cubed over 3. So that's 1 minus 1 over 3, which is equal to 2 thirds. So we have here 2 thirds minus 0 minus 0 cubed over 3. That's just 0. So we have 2 thirds here. Plus, for this one right here, we have 2 cubed over 3. That's 8 over 3. Minus 2, which we can write as 6 over 3. So we have here 2 thirds. 2 thirds minus, what we have here is 1 cube over 3. So that's 1 third minus 1. This is just negative 2 thirds. So that's 2 thirds minus negative 2 thirds. Okay. So we have here 2 times 2 thirds plus, oops, sorry, this is 2 thirds minus negative 2 thirds, right? So we have 2 thirds minus negative 2 thirds, that's just 4 over 3. So we have 4 over 3 here. And 2 over 3 plus 4 over 3 is just 6 over 3, which is equal to 2. So that's 2 times 2, which is equal to 4. And this is problem number 3. Let's proceed to the next problem. For this one, we want to integrate the quantity 1 minus y squared all over the square root of 1 plus y dy. So let's look at the one inside the square root first. What we have here is a 1 plus y. And if you differentiate this one, so if we let this one to be equal to u, then your du will actually be dy only. So in a way, it might make sense to do a u substitution here. So let's try that one. We can let u to be equal to 1 plus y. And what we'll get here is du equals dy. So the one inside, the 1 plus y, becomes u. This dy right here becomes du. Our problem right now is that we have a 1 minus y right here. But luckily, it is just easy to rewrite 1 minus y in terms of u. So looking at this one right here, we have u equals 1 plus y. And what we can do here is transfer this one right here. We get u minus y equals 1. And we can transfer u to the other side as well to get negative y equals 1 minus u. And finally, to get the 1 minus y here, we just add 1 to both sides. So we have 1 minus y equals 1 plus 1 minus u, or 2 minus u. So we'll get here integral of 1 minus y becomes 2 minus u. So you have 2 minus u squared. Then dy becomes du. And the square root of 1 plus y becomes square root of u. So that's all over square root of u. And luckily, this is a lot better since square root of u is just equal to u raised to 1 half. And this one above is something that is easy to expand. So let's expand this one first. We have 4 minus 2 times 2 times this one, 2 times u. So that's equal to 4u. So you have 4 squared. The one below is u raised to 1 half du. And by our laws of exponents, what we'll have here is 4 all over u raised to 1 half. So that's the same as 4 u raised to negative 1 half minus, you have 4u here all over u raised to 1 half. So that's 4u raised to 1 all over u raised to 1 half. And this one will just be equal to 4u raised to 1 minus 1 half, which is 4u raised to 1 half. 4u raised to 1 half. And for the other one, you have u squared all over u raised to 1 half. So that's u raised to 2 minus 1 half, which is u raised to 3 halves. So you have u raised to 3 halves du. And this one is quite easy to integrate. We will just use the power rule. So we have here 4 times u raised to negative 1 half plus 1. So get 1 half all over 1 half minus 4 times u raised to 1 half plus 1. That's 3 over 2 all over 3 over 2 plus u raised to 3 halves plus 1. That's u raised to 5 over 2 all over 5 over 2 plus c. And let's leave it as is. Let's not simplify it further. Oops! I forgot one thing. Remember that our problem is in terms of y. So what we have to do is plug back this one to our answer right here. So we have 4 times our u is 1 plus y. That's 1 plus y raised to 1 half over 1 half minus 4 times 1 plus y raised to 3 halves all over 3 halves plus 1 plus y raised to 5 halves all over 5 halves plus c. Okay? Now let's proceed to problem number 5. This one right here, we have to integrate 2x all over 5 minus 4x minus x squared dx. So as you can see from our problem here, what we tried to do is to express the one inside the square root as u. So maybe it might work. So if you let u to be equal to 5 minus 4x minus x squared, the du that you will get is negative 4 minus 2x dx. But our problem right here is that what we only have is a 2x dx. But here you have negative 4 minus 2x dx. So it might not be wise for us to do such thing. Instead, what we can do is try to complete the square in this one. And let's see what happens. So what we have here is a 5 minus 4x minus x squared. This one we can rewrite as the negative of negative 5 plus 4x plus x squared. Then reordering the one inside, we have the negative of x squared plus 4x minus 5. And to complete the square, what we just have to do is divide this one by 2. So you have 4 over 2. Then square that one. So we have 4 over 2 is 2. Then raised to 2 is 4. What we'll have here is x squared plus 4x plus 4. But since you added the 4, you have to revert that one. So you will also subtract a 4. And don't forget our minus 5 right there. So you have negative of x squared plus 4x plus 4 is just x plus 2 squared. Then minus 4 minus 5 will give you a minus 9. Then finally, distributing this negative sign right here, we have 9 minus the quantity x plus 2 squared. So this one right here, the integral of square root of 5 minus 4x minus x squared. Then in the numerator, you have your 2x. It's just the same as the integral of 2x all over the square root of 9 minus x plus 2 quantity squared dx. So why did we do this? Luckily, what you have right here is an expression with something inside, x plus 2. So this is actually better since if you let this one to be your u, then the du that you will get is just a dx right now. And this one right here is just a dx. So we have the integral of, so the one below is 9 minus u squared. Then your dx becomes a du. Now our problem is this 2x right here, but it's quite simple now. Remember, you have a u equals x plus 2, and so x would just be equal to u minus 2. And to get 2x, you just multiply both sides by 2, and you get 2x equals 2 times u minus 2, which is 2u minus 4. So what we'll have up here is a 2u minus 4. And one good thing about this is we can easily split our integral into two. First one would be the integral of 2u all over the square root of 9 minus u squared du. And for the other one, we have the integral of 4 all over the square root of 9 minus u squared du. And this is better since, as you can see here, you have a polynomial of degree 2. And if you differentiate this one, what you'll get is a negative 2u. And here, you have a positive 2u. So it's possible to do a u substitution there. So let's do it. For this first integral, we can let, let's say, 9 minus u squared. And so our dv would be the integral of, the derivative of 9 minus u squared, which is negative 2u du. And what we have here is a positive 2u du. So multiplying both sides by negative 1, we get negative dv equals 2u du. And so the integral of 2u all over the square root of 9 minus u squared du will just be this one here. 9 minus u squared is your v. So that's the integral of, you have a square root of v in the denominator. Then your 2u du will be a negative dv. And this one is just the same as negative integral of square root of v is just v raised to 1 half. And if you have 1 over v raised to 1 half, that's just the same as v raised to negative 1 half. So you have negative integral of v raised to negative 1 half dv. And the integral of this one is just negative of v raised to negative 1 half plus 1. So that's 1 half all over 1 half plus some constant, say c1. So we're done with the first integral. For the second one, it's actually simpler. For the second one, what you have is the integral of 4 over the square root of 9 minus u squared du. And this is just the same as 4 times the integral of du all over the square root of 9 minus u squared. And if you will recall, if you have an integral of this form, integral of du all over the square root of a squared minus u squared, where a is greater than 0, then the integral of this one is just sine inverse of u over a plus c. So following that one, what we have is 4 times sine inverse of u all over a. So if your a squared is equal to 9 and a is greater than 0, then that means a equals square root of 9, which is equal to 3. So you have u over 3 here plus some constant, say c2. And so this entire thing right here, this one right here, will just be equal to, for the first one, you have a negative v raised to 1 half over 1 half, but your v is 9 minus u squared, so that's negative 9 minus u squared raised to 1 half all over 1 half, plus you have here your 4 sine inverse of u over 3, then plus c1 plus c2, but remember the sum of two constants is just a constant, so we can just say that it's a constant c right here. And finally, plugging back your u equals x plus 2 right here, we have negative 9 minus the quantity x plus 2 squared raised to 1 half all over 1 half. Oops, we don't have space here. Plus 4 sine inverse of, you have x plus 2 all over 3 plus c. Okay? So the takeaway here is that if you have a quadratic in the denominator, it is best to do a completing the square. And from there, things become simple because you have something here that is a monomial most of the time. Or should I say, it's not a monomial. What we have here is a polynomial of degree 1. And that makes things a lot easier. Okay? Let's proceed to the second problem. Because of Padre Damaso's hatred towards the Western mindset of Crisostomo, Damaso locked Maria Clara inside a church bell tower. In order for Maria Clara to express her eternal love to Crisostomo, she wrote a message on a rock which Crisostomo must catch. Maria Clara threw the rock vertically from an elevation of 27 meters, and Crisostomo reaches out to catch the rock. If Crisostomo's outstretched arms are 2 meters high and the rock reach its maximum height after 2 seconds, when will Crisostomo catch the rock? For this one, we use negative 10 meters per second squared for the acceleration due to gravity. So let's see again the problem at hand. What we have is that Maria Clara is locked inside a church bell tower. So let's draw that tower here. Okay. And what we know is that Maria Clara threw the rock vertically from an elevation of 27 meters. So the rock started here at 27 meters. So that means if h is the height, if we let h be the current height of the rock, current height of the rock, or should I say, instead of h, let's call it h of t. Let h of t be the height of the rock at time t. Then this one right here at the very start, that means your t equals 0. What we have is that the height of the rock is 27 meters. The height of the rock initially is 27 meters. Then what Maria Clara did is she threw the rock, and after 2 seconds, its maximum height. After 2 seconds, its maximum height. Maximum height. And what will happen once you reach the maximum height? What will happen is that the rock will fall down. The rock will fall down until Crisostomo catches the rock. And what we know here is that Crisostomo's outstretched arms are 2 meters high. So right here, the height at this certain time, say capital T, is equal to 2. And what we want to do is to find this certain T such that Crisostomo catches the rock. So what we want is find this capital T. First, what we know is that the acceleration, so we know that the acceleration due to gravity is negative 10 meters per second square. So we let a of t to be equal to negative 10. Recall that given the acceleration, when you integrate this once, what you'll get is the velocity. Then integrating this once more, you get your height or your position. So first, we integrate this one to obtain the velocity. So we have v of t equals the integral of a of t dt, and that's the integral of negative 10 dt. And that one is just negative 10 t plus some constant, say c1. Now our problem is we have an unknown constant here. But luckily, what we know is that at t equals 2, at 2 seconds time, we have reached maximum height. And if you will recall, at maximum height, the particle stops momentarily, and that means the velocity at t equals 2 is 0. So since v of 2 is equal to 0, that means 0 equals v of 2, and v of 2 is just negative 10 times 2 plus c1. It comes from this equation right here. So that means 0 equals negative 10 times 2, that's negative 20 plus c1, and that means c1 equals positive 20. So what we have right now is that v of t equals negative 10t plus 20. Okay? Now, we have to solve for the height. And the height is just the integral of your velocity. So that's the integral of negative 10t plus 20 dt. So integrating this one, the integral of negative 10t, that's just negative 10 times t squared over 2 plus 20t plus another constant, say c2. Simplifying this a little bit, we have negative 5t squared plus 20t plus c2. Okay? What we know is that at t equals 0, your height is 27. So since h of 0 is equal to 27, that means that 27 equals h of 0, which is just the same as negative 5 times 0 squared plus 20 times 0 plus c2. So that means 27 equals, this one will be 0, this one will be 0. So you have c sub 2 equals 27. And that means, okay, I don't have space anymore, so I'll put it on this side. So that means that your h of t is negative 5t squared plus 20t plus 27. Okay? Now, our problem is this one right here. We need to find t such that h of t is equal to 2. So now, we find t such that h of capital T is equal to 2. So h of capital T is just negative 5t squared plus 20t plus 27. Then we equate this one to 2. Then transferring this one to the left side, we have negative 5t squared plus 20t, then plus 27 minus 2, that's 25, equals 0. And what we can do here is factor out negative 5. So you have your negative 5 multiplied by t squared. Then 20 divided by negative 5 is negative 4t. Then 25 over negative 5 is a negative 5. So you have t squared minus 4t minus 5 equals 0. This one right here, we can factor into negative 5 times. You can see that this one is t minus 5 times t plus 1 equals 0. And equating each factor into 0, from here we have t minus 5 equals 0, or t plus 1 equals 0. And solving for t, we have t equals 5 and t equals negative 1. Okay? But, since t is greater than or equal to 0, since we are talking about time here, what we have is t equals 5. So, our conclusion, so it takes 5 seconds for Crisostomo to catch the rock. Okay? I hope this one is clear. So for rectilinear motion problems, the first thing that you have to do is analyze what's happening in the problem. If it helps to draw it, then do so. Then from there, express everything mathematically. And what you do is just solve for, if for example the given is acceleration, then you have to solve for the velocity and the height, and you have to clear these constants right here. Okay? For the third problem, let f of x be this one right here. We need to determine f prime of x and find an equation to the line tangent to the graph of f at x equals -1. So to do this, we recall the first fundamental theorem of calculus. Let capital F of x be this one right here, where you have the function f, and for the bounds, you have a number a at the bottom and a function g of x at the top. Take note that the f here should be continuous on the closed interval ab, and g of x is within this interval. If g of x is differentiable, then we can talk about the derivative of this function right here, which is f of g of x multiplied by the derivative of the upper bound. So let's look at the given function. What we have here is f of x equals the integral of the square root of t times t squared plus 1 dt, where x goes from negative x to e raised to x plus 1. Okay. What we can see here is that this one right here is a function, so that's fine. But the one below is also a function, not a number. So outright, we cannot apply the first fundamental theorem of calculus. And so what we need to do is to split this integral into two. So we have here the integral from negative x to whatever number, say c, the square root of t times t squared plus 1 dt, plus the integral from c to e raised to x plus 1 of the square root of t times t squared plus 1 dt. For some c in the domain of your function f. So take note, the function f here is this one. So let's call this f of t. Okay? Now let's look at what is given. Here, what we have is a number on top and a function on the bottom. But for us to use the first fundamental theorem of calculus, what you need to have here is a number in the bottom and a function at the top. So we have to switch the bounds, and by switching it, we negate our integral. So you have the negative integral from c to negative x of the square root of t times t squared plus 1 dt, plus the integral from c to e raised to x plus 1 of the square root of t times t squared plus 1 dt. Okay? So now, we can apply the first fundamental theorem of calculus to our integral here. F prime of x would be equal to, what we will do is plug this one inside. So you have the square root of negative x multiplied by negative x raised to 2 plus 1 times the derivative of this one. So the derivative of this one is -1. Oops, I forgot the negative sign here since we have a negative sign right here. Then plus the square root of, we will plug this one inside. We have e raised to x plus 1 multiplied by e raised to x plus 1 squared plus 1 multiplied by the derivative of this function right here. And the derivative of that one is e raised to x plus 1 multiplied by the derivative of x plus 1, which is just 1. Or simplifying further, we have the square root of negative x times x squared plus 1 plus the square plus e raised to x plus 1 square root of e raised to x plus 1 times e raised to x plus 1 squared plus 1. Okay? So we're done looking for f prime of x. Now, we need to find an equation to the line tangent to the graph of f at x equals negative 1. So for us to do this one, we need first the value of f at x equals negative 1, and we also need the value of f prime at negative 1, since this one here will serve as the slope of our tangent line. Okay? So for the tangent line, first we need your f of negative 1, and that one would be the integral from, so we will plug negative 1 to the bounds, so that's the negative of negative 1 to e raised to negative 1 plus 1 of the square root of t times t squared plus 1 dt. But this one here, the one below negative of negative 1 is just a positive 1, while here, what we have is e raised to 0, which is equal to 1. So we have the integral from 1 to 1 of the square root of t times t squared plus 1 dt. And since the bounds are the same, automatically this integral will just be 0. So f of negative 1 equals 0. Next, what we need is your f prime of negative 1. So f prime of 1, we'll just plug negative 1 right here. We have the square root of negative 1 times negative 1 squared plus 1. Okay. Plus e raised to negative 1 plus 1 square root of e raised to negative 1 plus 1 times e raised to negative 1 plus 1 squared plus 1. Okay? This one here would be positive 1 times 1 squared plus 1, which should be equal to 2. So we have here square root of 2 plus e raised to negative 1 plus 1, so that's 1, times the square root of e raised to negative 1 plus 1, that's e raised to 0 equals 1, plus 1 squared plus 1. So that's the square root of 2 plus square root of 2, and we get here 2 square root of 2. Let's double check. This is positive 1 times 1 plus 1. Okay, that's 2. Then here inside, we have 1 times 1 squared plus 1, which is also square 2. So you have square root of 2 plus square root of 2 equals 2 square root of 2. And now, for the equation of the tangent line, this one would just be y minus y sub 0 equals the slope times x minus x sub 0, right? So this is the equation of the tangent line. Equation of the tangent line. Here, your y naught would be f of negative 1, so that's y minus 0, or y equals, for the slope, that would be your f prime of negative 1, so that's 2 square root of 2 multiplied by x minus x naught. So your x naught is -1. So that's x minus -1. And finally, rewriting this, we have y equals 2 square root of 2 multiplied by x plus 1. Okay? I hope this one is clear. Let's proceed to the next problem. Okay. For number 4, let R sub 1 be the region in the first quadrant bounded by the curves x squared plus y squared equals 3 and y squared equals -x plus 3. So what we are talking about is this region right here. And we let R2 be the region in the first quadrant bounded by the curves C1, C2, and the coordinate axis. So what we are talking about is this one right here. For the first part, rewrite the two curves in the form y equals f of x. So let's start with C1. So your C1 is x squared plus y squared equals 3. What we just have to do is write it in the form y equals f of x. So we transfer this one here. We get y squared equals 3 minus x squared. Then obtaining the square root of both sides, we have y equals plus minus square root of 3 minus x squared. However, take note that we are considering the first quadrant. And in the first quadrant, the values of y are positive. So we are dropping this one and retain the positive. So this is positive since in quadrant 1, y is greater than or equal to 0. Okay? Then for the second one, what we have is y squared equals -x plus 3. So same thing, we just obtain the square root of both sides. We have y equals plus minus square root of minus x plus 3. Now take note that what we have here are positive values of x since we are in quadrant 1. And the values of y should also be positive. So we are dropping the plus and minus and retain the positive for the same reason. Okay? So for letter B, what we need to do is find the intersection points of C1 and C2. So I think it's better if we stick to the original form. What we have here is x squared plus y squared equals 3 and y squared equals -x plus 3. So to find their intersection points, we can plug this one in the y squared right here. So that will have x squared plus -x plus 3 equals 3. Then simplifying this, we have x squared minus x plus 3 equals 3. Then transferring this to the left side, we have x squared minus x equals 0. Then finally, solving this quadratic, we can factor the left side into x times x minus 1, then equals 0 for us to be given x equals 0 and x equals 1. Now, if x equals 0, what do we know? So, if x equals 0, we can use the first curve and plug x equals 0 there. We have 0 squared plus y squared equals 3, which would give us y squared equals 3. Then obtaining the square root of both sides, we have y equals square root of 3. Again, it's positive because we are considering the first quadrant. Positive since we're in the first quadrant. Then for the second one, if x equals 1, then we have 1 squared plus y squared equals 3. This would give us y squared plus 1 equals 3. And that's equivalent to saying that y squared equals 2 and obtaining the square root of both sides. We have y equals positive square root of 2. Okay? Then next, let's proceed to the third problem. For the third problem, we need to set up the integral that gives the perimeter of your R2 right here. Okay? First, let's plug our intersection points so that we don't forget them. First one, if x equals 0, y equals square root of 3, that's this one right here. So this is your 0 square root of 3. Then this one right here, another intersection point, that's 1 square root of 2. Now, let's recall our circle. So if the equation of your circle is x squared plus y squared equals 3, that means that you have a circle with center 0, 0 and radius square root of 3. So if the center is 0, 0 and you have a radius of square root of 3, then this one right here has length square root of 3. Here has length square root of 3, and this point right here is actually square root of 3 comma 0. So if this one is 0, 0, this one is square root of 3 comma 0, then the length of that one is square root of 3. Then same thing here, 0, 0 to 0 comma square root of 3, we have length square root of 3. So for the first one, our perimeter is square root of 3. This one comes from the x-axis part. Then another square root of 3 from the y-axis part. Y-axis part. Okay? I'll just put it here since we will do more calculations. Our problem right now is this curve right here and this other curve right here. Okay? So what we have again for the blue curve is the parabola. What we have is y equals square root of negative x plus 3. So the blue curve is y equals square root of negative x plus 3. And we are obtaining its arc length from x equals 0 to x equals 1. We are obtaining this from x equals 0 to x equals 1. Okay, let's try and recall the formula for your arc length. Suppose you are given a smooth function. So when you say smooth function, that means f is continuous. And, if we say smooth, that means f is differentiable and its derivative f prime is continuous. So suppose you have a smooth function f, then the arc length is the integral from a to b of the square root of 1 plus the square of its derivative, dx. Okay? So following that formula, it's telling us that we need to obtain the derivative of this one. So the derivative of this one would just be 1 all over 2 square root of negative x plus 3 multiplied by the derivative of the one inside, which is negative 1. And for the red curve, that's your circle. Our equation is y equals the square root of 3 minus x squared. So that's square root of 3 minus x squared. And we are obtaining the arc length from x equals 1 all the way to x equals square root of 3. So from x equals 1 to x equals square root of 3. So let's obtain the derivative of this one. So y prime equals 1 all over 2 multiplied by the square root of 3 minus x squared multiplied by the derivative of the inside, which is negative 2x. So we can do this now. Let's set up the integral. For the blue curve, that would be the integral of the square root of 1 plus its derivative right here. So that's negative 1 over 2 square root of negative x plus 3 squared dx. And the bounds would be from x equals 0 to x equals 1. 0 to 1. This is for the blue curve. Blue curve. And for the red curve, this would be the integral of the square root of 1 plus its derivative, negative 2x all over 2 square root of 3 minus x squared dx. And our bounds would be from x equals 1 to x equals square root of 3. X equals 1 to square root of 3. This one is for the red curve. Okay? So the perimeter of this one, the length of the part in the x-axis, square root of 3. Then for the y-axis, that's square root of 3. Then this one's for the blue curve. And this one is for the red curve. Okay? Let's copy this figure since we will need it in the next page. Okay. There you go. Paste. For letter D, set up the integral that gives the area of the union of r sub 1 and r sub 2. So we will obtain this area right here. Then we indicate whether we use vertical or horizontal rectangles. So for this one, let's try to use both of them. So let's first using vertical rectangles. So let's recall vertical rectangles. If we are doing vertical rectangles, in order for you to sweep the region, you are moving from left to right. So this means we move from left to right, and moving from left to right means that we are moving through values of x. So we are moving through x, so our area should be in terms of x. Okay? Luckily, our functions are written in terms of y equals f of x. Let's put them here for C1. Your y equals, what's that one again? Square root of 3 minus x squared. Then for C2, your y equals the square root of negative x plus 3. Negative x plus 3. Okay? So for us to set up this integral, we will do it for both the first region and the second region. So let's obtain first the area of the first region. For the first region, it is consistent that the top curve is the red one and the bottom curve is the blue one. So we only have to set this one up just once. So we have the integral of the red curve. The red curve again is the circle. So that's the square root of 3 minus x squared minus the bottom curve. The bottom curve is the blue one, which is square root of negative x plus 3. Square root of negative x plus 3 dx. So again, this is the top curve minus the bottom curve. And for the bounds, what bound we are considering are values of x. So we are moving from x equals 0 until we reach x equals 1. So we have here from 0 to 1. For R2, however, there are two cases. The first one is this one right here, where the top curve is the blue curve and the bottom curve is your x-axis. And for the second one, your red curve will be the top curve, and the bottom curve is still the x-axis. So we set this one up twice. First one is for this one, that's top curve minus bottom curve. Recall that your x-axis has equation y equals 0. So that's the blue curve, square root of negative x plus 3 minus the bottom curve, that's 0. So top curve minus bottom curve dx, and the bounds would be from x equals 0 until this part right here, x equals 1. So that's from 0 to 1. And for the second setup, it would be this one. So that's the red curve minus your x-axis. For the red curve, that's the square root of 3 minus x squared. Then minus 0 for the bottom curve. So top curve minus bottom curve. And we are obtaining the area from this part right here, x equals 1, until you reach this part right here, x equals square root of 3. So you have here from 1 to square root of 3. And so your area would just be the area of R1 plus the area of R2. And that one would be this one right here. I'll just copy it. Okay, I hope I'll copy it perfectly. So it's this one. Oops. Plus. Okay, I'll just copy the entire thing. Plus this one right here. And obviously it doesn't fit. Okay. It's this one right here. Plus. Okay? I hope letter D is clear. Oops. So now let's try horizontal rectangles using horizontal rectangles. So for us to use horizontal rectangles, they look like this. And for us to span the entire region, we are moving from the bottom to the top. So we are moving from bottom to top. And since we are moving from bottom to top, that means that we are moving through values of y. So we have to make sure that our setup is in terms of y. Now going back, our functions are of the form y equals f of x. So the challenge now is to write our functions in the form x equals f of y. Okay, let's do that right here. I hope it still fits. Okay. Here. So for the first curve, your circle x squared plus y squared equals 3. For us to write this one in the form x equals f of y, we just move this one to the right side. We get x squared equals 3 minus y squared. Then obtaining the square root of both sides, we have x equals plus minus square root of 3 minus y squared. So that's plus minus. But since x is greater than or equals to 0, that means we are dropping the negative sign. So we retain the positive 1. For the second curve, we have y squared equals negative x plus 3. So to solve for x, we just move it here so that it becomes positive. This one, we move it right here. So we get positive x equals 3, then the y squared becomes a negative. Okay? So let's set up for the area of region 1 here. It is consistent that the right curve would be the red one and the left curve would be the blue one. So what we will do here is just a single setup. That would be the integral of the right curve minus the left curve. So for the red one, that's the square root of 3 minus y squared minus the left curve, 3 minus y squared. And this time, instead of dx, it becomes dy. And for our bounds, we are doing this from the lowest y value, y equals square root of 2, until we reach this point, y equals square root of 3. So this one would be from square root of 2 up to square root of 3. And for the second region, again, there are two cases. First one is this one right here, where your right curve is the blue curve and your left curve is the y-axis with equation x equals 0. For this one, the right curve is the red curve and the left curve is x equals 0. So let's do the setup. That's the integral of the one here. So we start from the blue curve until x equals 0. So that's 3 minus y squared minus 0. So that's the right minus left. I'll just put it right here also, right minus left. So dy. And we are doing this from this point right here until this one right here. So that's still from y equals square root of 2 to y equals square root of 3. So this is from y equals square root of 2 to y equals square root of 3. Plus, for the second one, it would be the red curve minus the y-axis. So that's the square root of 3 minus y squared minus 0. This is your red curve, the right curve, and your left curve is the y-axis, x equals 0. And dy, and for our bounds, we are doing it from this level right here with y equals 0 until this one with y equals square root of 2. So that's from 0 to square root of 2. For letter E, we use geometry to find the area of the region R. Use the area of R to show that the area of R1 is this one right here. And note that we are given the value for this certain integral. So since the one given here is in terms of x, we will use the one that we set up using vertical rectangles. So we have this one right here. Let's lift it to the next page. Okay. Now, let's try and see what the region R really is. So recall that the region R is the area of the union of R1 and R2. This one here is R1, while this one right here is R2. And as we can see, we are talking about this quarter circle right here with radius square root of 3. So R is the quarter circle of radius square root of 3. And so the area of R should be equal to, first, the area of the circle, so that's pi times the radius square root of 3 squared, But since it's a quarter circle, we have to divide this one by 4. So square root of 3 squared, that's 3 times pi over 4. We have 3 pi over 4. Now, what we want to look for is the area of R1. So this is what we want to look for. This is your area for R1. So what we know is that the area of the entire R is just the area of R1 plus the area of R2. And so, if we want to obtain this area only, what we can do is obtain the area of the entire region, but we remove this one right here. So, what we know is that the area of R1 is just the area of R minus the area of R2. And the area of R, that's what we obtained, that's 3 pi over 4. Then minus the area of R2. And the area of R2 is this one right here. So that's minus the integral from 0 to 1 of the square root of negative x plus 3 dx plus this one right here. The integral from 1 to square root of 3 of the square root of 3 minus x squared dx. And we are given this one as the value of that integral. So let's plug it in. You have 3 pi over 4 minus 3 sine inverse of 1 over square root of 3 plus the square root of 2 all over 2. Okay? So now, our problem is this integral right here. Okay, let's solve that one first. You have the integral from 0 to 1 of the square root of negative x plus 3 dx. And observe that the derivative of this one right here is negative 1. And that's quite good since what we have is a constant multiple of the one outside. So let's do a u substitution with u equals negative x plus 3. Then your du here would be the derivative of this one, which is negative 1 multiplied by your differential in x. And so your dx would be just negative of du. Now, since we are doing a u substitution, we have to correct our bounds right here. So first, if x is equal to 0, let's find the value for u. So u equals negative 0 plus 3, and that's just 3. And if x equals 1, then u equals negative 1 plus 3, so that's a positive 2. So we have here the integral from, instead of x equals 0, it becomes u equals 3. So you have integral from 3 to 2 of the square root of the square root of negative x plus 3. It becomes square root of u. Then your dx right here becomes a negative du. Negative du. And since this is a constant multiple, we can put that outside. We have negative integral from 3 to 2 of the square root of u du. And this one here, since 3 is bigger than 2, we can switch the bounds. But by switching the bounds, we are introducing a negative sign here. And the negative times a negative would be a positive. So we have the integral from 2 to 3 of square root of u du. And the integral of square root of u, that's just u raised to, recall that u is, a square root of u is just u raised to 1/2. And the integral of this one would just be u raised to 3 over 2 all over 3 over 2. Evaluated from u equals 2 to u equals 3. We still have space. Okay. let's move this up here. Okay. So plugging u equals 3 and u equals 2, what we'll have here, first we have 1 over 3 halves. So that's just 2/3. You have 2/3 multiplied by, first we have u raised to 3 halves. So that's 3 raised to 3 over 2. And 3 raised to 3 over 2 is just the same as the square root of 3 raised to 3. And this one here is just the same as the square root of 3 squared times 3. And the square root of 3 squared is the same as 3. So this one should be 3 square root of 3. So this one here is 3 square root of 3. Then minus, now for u equals 2, we have 2 raised to 3 halves, which is the same as the square root of 2 raised to 3. The same as 2 squared times 2. So that's 2 square root of 2. So you have 2 square root of 2. And this is just the same as 6 square root of 3 minus 4 square root of 2 over 3. So what we did here is we just multiplied 2 to each term right there. So we can plug that value that we obtained. We have 3 pi over 4 minus, this one becomes 6 square root of 3 minus 4 square root of 2 all over 3 plus 3 pi over 4 minus 3 sine inverse of 1 over square root of 3 plus square root of 2 all over 2. Okay? So let's simplify this further. You have a negative sign here, so we can distribute it inside. Minus 6 square root of 3 minus 4 square root of 2 all over 3. This one becomes a negative 3 pi over 4. And you have a positive 3 sine inverse of 1 over square root of 3 plus square root of 2 all over 2. So you have here a 3 pi over 4 minus a 3 pi over 4. So we can just get rid of that one. And now we add up these two fractions right here. So you have a denominator of 3 and the denominator of 2. So your least common denominator would be a 6. Now 6 divided by 3 would give you a 2. Multiplied by this entire thing right here. Take note that you have a negative sign. That's negative 2 times 6 square root of 3 minus 4 square root of 2. Then for the second term, 6 divided by 2 would give you 3. So that's 3 multiplied by 3 sine inverse of 1 over square root of 3 plus square root of 2. So let's further simplify this one. For this part right here, negative 2 times 6, then negative 2 plus times negative 4 is a positive 8. So that's negative 12 square root of 3 plus 8 square root of 2. Then for this side right here, 3 times 3 is 9. So that's 9 sine inverse of 1 over square root of 3. Then you have 3 times square root of 2. That's 3 square root of 2 all over 6. So what we have here now is your 9 sine inverse of 1 over square root of 3. 9 sine inverse of 1 over square root of 3. Then you have a positive 8 square root of 2 here plus a positive 3 square root of 2. So that's a positive 11 square root of 2. Then you have your minus 12 square root of 3 here. Minus 12 square root of 3. Then in the denominator, you have 6. And that's what we want to show here. Okay? So letter E, that's quite Easy as well. Now let's proceed to letter F. We'll need our diagram again here. Okay. Oops. Okay. For letter F, we need to set up the integral that gives the volume of the solid generated by revolving, for the first one, R1 about the line y equals 2. So the line y equals 2, that's something that is above y equals square root of 3. So let's just move this one a little bit. And this line right here should be y equals 2. And what we want to do is revolve this region right here about this line. So let's recall your washer's method. Washer's method. So suppose you have your outer radius or not. This is your outer radius. And you have your inner radius r sub I. Inner radius r sub I. Then the volume should just be the integral of your outer radius squared minus inner radius squared multiplied by pi. And we will differentiate this with respect to whatever variable. So I'll just put x or y. And we do this for the corresponding bounds for x and y. Okay? So that's your washer's method. For this one, what we have is a horizontal line. And if you recall, if we're doing a washer, we're doing this in this manner. And let's put the hole here. This is your entire washer. So the rectangles that you are using to measure the radius should be a vertical one. And since you're using a vertical one, in order for you to span the entire region, you need to move from left to right. And so we are doing this through values of x. Okay? So what we have here is a horizontal axis. And using a horizontal axis would require you to use vertical rectangles. And vertical rectangles, that means we are moving through values of x. So first, let's identify our outer radius. So if you draw the washer, it would be something like this. So your outer radius would start from the blue curve until it reaches y equals 2. So that's your outer radius. So we have here v equals the integral of, so for the outer radius, since we are using vertical rectangles, to compute for that one, it would just be the top curve minus the bottom curve. So top curve is 2 minus the bottom curve. We are talking about the blue one right here, which is your parabola with equation, where's that? This one right here. Y equals the square root of negative x plus 3. Okay? So that's the square root of negative x plus 3. And we are integrating with respect to x since we are using functions in terms of x here. And as for your bounds, oops, we are not yet done. Sorry about that one. So that's your outer radius. Okay. And we have to square this one. Minus the inner radius. So your inner radius would be from this red one right here to the axis. So top minus bottom curve, that's 2, minus the equation of the circle, that's y equals square root of 3 minus x squared. So that's square root of 3 minus x squared raised to 2. And we are integrating with respect to x. And we are moving from this portion right here until you reach this one right here. So our bounds are from x equals 0 until we reach x equals 1. So that's from 0 to 1. Oops, I forgot the pi right here. Okay? So for Washer's method, that would be always pi multiplied by your outer radius squared minus the inner radius squared. And if you are using vertical rectangles, what you're doing is you're subtracting the bottom curve from the top curve. So that's top minus bottom. This one here as well. Top minus bottom. Okay? So let's proceed to letter B. So for letter B, what we want to do is revolve the region R2 about the line x equals 0. So this is R2. This is your R2 right here. And we want to revolve it about the line x equals 0. So we want to revolve it about the line x equals 0. And the line x equals 0 is this one right here. Okay? That's x equals 0. The problem with R2, so let's try to imagine the washer. Unfortunately, we don't have space right here. So we will just draw a washer somewhere right here. So I'll take this and draw half a washer. So this is a half washer here. The problem is, in this part, your radius would be from the blue one until this one already. However, for the red part right here, you have a different radius. It would start from here until it reaches the axis. So this is the appearance of your washer. Okay? So we have to split our integral into 2. So let's divide it right here. And we obtain the volume separately. So we obtain the volume of this part right here. Then we just add the volume of this one right here. So take note, we are using now a vertical axis. Vertical axis. So when you measure your washer, you're starting from here until here. What you are using are horizontal rectangles. So you are using horizontal rectangles. And since you're using horizontal rectangles, for you to span the entire region, you'll be starting from the bottom part until you reach the top part. So that means we are moving through values of y. Okay? So we have to make sure that our functions are written in terms of y. So we have done that a while ago. For C1, that's x equals 3 square root of 3 minus y squared. Then for C2, it's x equals 3 minus y squared. Okay, let's do the first part. This one right here. So luckily, your axis is in the boundary of the region. So that means you don't really have a hole in your washer. So let's have a sort of a top view, I guess. This is your axis and this is your curve. Okay, this is the other boundary for your washer. So if you revolve this only boundary with respect to the other boundary, which is an axis, what you only have is a single circle. So that means there's no outer radius, there's no inner radius, you only have one radius. And since you only have one radius, we can think of it already as the outer radius. So we just remove this one, you just have pi times the radius squared. So for the first part, you have pi times the radius here, that's the red curve, until you reach x equals 0. So that's 3 minus y, no, it's this one. X equals square root of 3 minus y squared, square root of 3 minus y squared, minus the left curve. So that's the right curve minus the left curve. But your left curve is x equals 0 squared. And since our functions are in terms of y, we are integrating with respect to y. And for your bounds, we are moving from here, y equals 0, until you reach this part right here, y equals square root of 2. So you have y equals 0 to y equals square root of 2. Okay? So this is your right curve minus left curve. And we're doing it for this region here. So let's call it R2A for reference. And this one is R2B. So we are doing that for your region R2A. And for the second one, it's the same situation as what we observed a while ago. You only have one radius since the axis is part of the boundary of this region. So to obtain this radius here, you just subtract the right curve from the left curve. And the right curve is this one. X equals 3 minus y squared. So you have 3 minus y squared minus the equation for the left curve, which is x equals 0. And same thing, since this is in terms of y, we are integrating with respect to y. And, oops, I forgot the pi again. And the squared, so that's pi radius squared. And as for your bounds, we are starting now from this one, y equals square root of 2, until you reach the top, y equals square root of 3. So from y equals square root of 2 to y equals square root of 3. So that's right curve minus left curve for the radius of your region 2B. Okay? So once again, for washers, it's just pi multiplied by outer radius squared minus inner radius squared. But in the event that you don't have an outer or an inner radius, then it's simply pi times the radius squared. Okay? And at last, we are done with this region. Let's proceed to the next problem. Okay, this one right here. For the fifth problem, we want to show that the volume of a pyramid with square base, so we have the length s and height h, is v equals s squared h over 3 using horizontal slices. So let's recall volume by slicing. Volume by slicing. So what we are doing here is, you have a solid here and you want to obtain the volume of this one. So what you can do is consider a cross section right here. So what we are doing is a vertical slice. And for us to span the entire solid, you need to obtain slices from left to right. So if it's vertical slice, what you need is obtain the area of your cross section. So once again, this is the solid. You are slicing right here, for instance, and you're doing it from left to right. So that means you are moving through values of x. So this one should be in terms of x, and you're integrating from the leftmost to the rightmost. But if you're doing a horizontal slice, so for example, you have this solid right here, you want to obtain the volume of this one, so you do a slice right here vertically and obtain the area from the bottom part to the top part. So we are moving through values of y. Your v would be the integral from the bounds of the area, but this time it should be in terms of y. Okay? So what we are doing here, based on the instructions, are horizontal slices. So you have your pyramid with a square base. You have a pyramid with your square base. Oops. Let's see. Okay? I hope I can get this right. Let's just convince ourselves that this is a square. I'm not that good at drawing actually. So you have your pyramid right here that doesn't really look that right. Okay. So this is your pyramid with the square base with length s. So the length of this one right here is s, and it has a height of h. When we slice this horizontally, for example here, what we expect to see is a square as well, right? So let's start first. If your h equals 0, then we are talking about the base. We are talking about the base with side s. But for any h, or for any y rather, for any y in the interval 0 to h, once again, if you slice a pyramid horizontally, what you'll expect is a square, right? So you'll get a square, but this time, oops, you will expect that your region will shrink, right? Or the side of the square will shrink. So let's call the side of this one s of y. Okay? What our goal is to find this s of y and express it in terms of the values that we know. That is, we have your s and h, which is the height of your pyramid. Oops, to make this not confusing, let's call it y instead. Y equals 0. So let's try and see what happens. So for example, right here, if you start with the bottom portion, you know that you have a triangle with a base of s, right? And if this is a square, what you'll expect is that you have an isosceles triangle right here. So that's s with the height of h. Okay? So we expect here that you have a triangle with base s and a height of h. And a height of h. However, if you slice right here, what you'll get is still a triangle, but your triangle now would have a base of s of y, since this one corresponds to the length of your square, and this one right here, so let's try and draw your triangle here. So this is of height h. Suppose you slice it at some value of y. So what we know is that this height would be y, And so this one right here should be h minus y. So this one here, it's still a triangle, but this time you have a base of s of y and a height of h minus y. But in both cases, what you have right here is a right triangle. And since we are only scaling, the angles will be preserved. So this angle right here is preserved. This angle is preserved. This angle is preserved. And you have your side here. So we can invoke the similarity of triangles. So by the similarity of these two triangles, the similarity of triangles, we can talk about the ratio of the height with respect to the base right here. So height over the base. So we have height here of this triangle, which is h, divided by the length of the base, which is s. And we expect this one to be equal to this height divided by this base right here, s of y. And we solve for s of y here by cross multiplying. We have h times s of y equals h minus y times s. Then dividing both sides by h, we get here s of y equals s times h minus y all over h. Okay? So now, we can obtain the volume. So your volume then would be the integral. So the area, the cross-sectional area would be s of y squared. That's the area of your square. So that's s of y squared dy. And as for the bounds, we are starting from the bottommost, which is of height 0, until we reach the very top with height h. So that would be from 0 to h. But your s of y is this one right here. So we have the integral from 0 to h of s times h minus y over h squared dy. Then distributing the square towards these factors here, we will have integral from 0 to h of s squared times h minus y squared all over h squared dy. And what we know is that this value of s here is fixed, and this value of h here is also fixed. So we can bring them outside. You have s squared over h squared multiplied by the integral from 0 to h of h minus y squared dy. Okay? Now to solve for this one, we can apply a u substitution with u equals h minus y, because the differential of u that you will obtain is the derivative of this one with respect to y, which is negative 1 times dy. And so your dy then would be equal to negative du. Once again, we are doing a definite integration here, so we have to change the bounds. So first, if y equals 0, then your u would be equal to h minus 0, which is equal to h. While if y equals h, then u equals h minus h, which will be equal to 0. So we have here s squared over h squared multiplied by the integral from y equals 0 will be changed to y equals h. Then y equals h would be changed to u equals 0. So that's the integral from h to 0 of u squared. But you have your negative sign here, so that's negative du. Then you have a negative sign here, which we can distribute outside. So this becomes u squared du, and you have your negative right here. But since h is a non-negative value, we have to switch the bounds. But by switching the bounds, you're introducing a new negative sign. So you have here 0 to h of u squared du. Then you have the negative of negative s squared over h squared. So negative times a negative, they just cancel each other out. So this becomes a positive s squared over h squared. Okay? So the integral of u squared is u cubed over 3. And we are evaluating this from u equals 0 to u equals h. So we have here s squared over h squared multiplied by, we plug h, so that's h cubed over 3 minus, if u equals 0, we get 0 cubed over 3. So that's a minus 0. Let's just not add that one anymore. So we have h cubed over 3 here. Then we have here h cubed divided by h squared. So that will give us h. Then you have your s squared factor there. And in the denominator, you still have your 3. And so the volume of this pyramid right here is s squared h over 3. Okay? So let's proceed to the last part, the true or false. So for true or false, always remember this one, no? If we say true, this means that for any possible scenario under the given assumption, the statement is true. The statement is true. But if you say false, that means there is a single scenario that makes the statement false. That makes the statement false. So that means if you say that the statement is true, it should be true for any possible scenario. But to say that a statement is false, it's enough to find a single example or a single scenario that makes your statement false. Okay? So let's proceed to letter A. Letter A, what this one is telling is the function f of x equals the integral from negative x to 1 of f of t dt is an antiderivative of the continuous function f of x. So recall, f of x is an antiderivative of small f of x. That just means that the derivative of your capital F is the small f. Okay? So to check if this one is an antiderivative of small f, we just have to differentiate this function right here. So we are given f of x equals the integral from negative x to 1 of f of t dt. So to obtain this derivative, if you will recall from a while ago, we have to make sure that the bottom bound is a number and the top bound is a function. But in this case, it is the reverse. The lower bound is a function and the upper bound is a number. So we have to change bounds. So by doing so, you will introduce a negative sign, and you have the integral from 1 to negative x of f of t dt. And so by the first fundamental theorem of calculus, the derivative of this one is f of, oops, you have a negative sign here, negative of f of, you will plug this one inside f, so you have negative f of negative x multiplied by the derivative of this one, which is negative 1, which is equal to f of negative x. Okay? The problem right here is that for this to be an antiderivative of f of x, the derivative should be f of x. But what we have seen is that the derivative of big f of x is f of negative x. So take note that in general, f of negative x is not equal to f of x. Okay? This only happens if f is even. But what we said is that the function f is a continuous function. So we didn't say whether it's even or odd. So, but we only assumed that f is continuous. Therefore, we have some scenarios that makes the statement false. That is, if your f is odd or f is neither odd nor even. So our answer here should be false. Answer here is false. Okay? So let's proceed to letter B. For letter B, if f is an integrable function on the closed interval AB, then f is differentiable on the open interval AB. So let's recall this implication. Differentiable implies continuous, implies integrable. Okay? So that means if we will draw the diagram for that one, what you have inside here are the set of differentiable functions. Then here you have the set of continuous functions. And finally here, you have the set of integrable functions. What this is telling us is that it is possible to find an integrable function that might not be continuous and might not be differentiable. It's also possible to find a continuous function that is not differentiable. However, since it is continuous, we are sure that it is integrable. But in this case, it is not differentiable. So what we can do, let's try and think of a function that either is integrable but is not differentiable, or if you cannot think of that one, you start with a continuous function that is not differentiable. And luckily, we have an example for this one. So if you recall, this function right here, absolute value of x, is continuous at x equals 0, but it is not differentiable at x equals 0. So for example, if we consider the interval -1 to 1, and the function f of x equals absolute value of x, we have that f is continuous on this entire interval, and so f is differentiable. F is integrable, rather. F is integrable. But f is not differentiable on the entire interval, or -1 to 1, since f is not differentiable at x equals 0. And so, our answer to this one should be false. Okay? This is false since we have shown that there is a certain scenario which makes this statement right here false. Okay? Now, let's proceed to letter C. So, for letter C, if A is less than B and f is continuous on the closed interval AB, and f prime of x equals f of x on the closed interval AB, then this integral right here should be equal to this one. So this is quite a lot. You see two integration signs, so let's just do this step by step. So we have here the integral from a to b of the integral of a to b of f e, and we're integrating this with respect to x. So what we know is that f is continuous on this closed interval AB. So we can apply the second fundamental theorem of calculus, and it states that this integral right here should just be the difference of their antiderivatives evaluated at these 2 points. So you have integral from a to b of this one right here. What we know is that f is an antiderivative of your small f. So that would be f of b minus f of a, since the upper bound is b and the lower bound is a. And we have to integrate this one with respect to x. Take note, however, that this one right here is already a constant. This one here is also a constant. So this entire thing is a constant, and since it's a constant, we can bring this outside. So we have here f of b minus f of a multiplied by the integral from a to b of dx. And by our theorem, this one right here should just be b minus a. So you have f of b minus f of a multiplied by b minus a. And this one right here is this one. So we have shown that this statement right here is true. So the answer is true. Okay? So let's proceed to letter D. Letter D, if f of x is a function and c is in the domain of f, then this integral is f of c times b minus a. So it's actually just the same as letter C. Observe that this integral right here, since c is in the domain of f, we know that this is existing, and furthermore, it is a constant. Exists since c is in the domain of f, and therefore this is a constant. So we can just move that outside. You have f of c times the integral from a to b of dx. And so, we have here f of c times b minus a. So the answer is true. Lastly, for letter E, what we have here, if n is a positive integer and k is in between 0 and 1, then this integral right here is equal to n times k. So let's recall your greatest integer. Write it in its piecewise form. That it's 0 if 0 is less than or equal to x, less than 1, 1 if 1 is less than or equal to x, less than 2, so on and so forth. And here, negative 1 less than x, less than 0, so on and so forth. Okay? So for any n here, if you will make this n, then this one will be n, and this one is n plus 1. So this one would be equal to n for x within this interval right here, n to n plus 1. Okay? That's what this statement is saying here. If you change this to n, becomes n, this is n plus 1. So our corresponding interval is close on this side since we are including n, but we are excluding n plus 1. So it's open on this side. Okay? Now, the k that we are considering is in between 0 and 1. Okay? So take note, k is in between 0 and 1. And the bound that we are considering here is n plus k. So that means n plus k in between n and n plus 1. So what this is telling us is that for the bound n to n plus k, it is consistent that the greatest integer of x would just be n. Okay? So take note that for any number here, we are sure that it would be in between n and n plus 1. Since if you start here, you have n less than or equal to n less than n plus 1. But if you consider the extreme uppercase, we have that n plus k is in between n and n plus 1. So, by this definition right here, this is telling us that for any number inside this one, your greatest integer value of x would just be n. And so, the integral of the greatest integer of x with respect to x from n to n plus k, we can replace that to the greatest integer, or should I say the integral from n to n plus k of n dx. And since this is a constant, we can just put that outside. You have n times the integral of dx from n to n plus k. So this one would be n times the the integral of this one is just your upper bound minus your lower bound. So that's n multiplied by n plus k minus n. What you'll have is k right here. And so that is what we are expecting right here. The entire integral will be equal to nk. And so the answer here is true. And that ends our video here. So if you have any questions, you can put that in the comment section, or for my students, you can message me. So thank you and good luck on your exam.